Okay, so I think we can get started. So, well, thank you everyone for coming, and thank you to every CTF player for playing. This is the Dragon Sector team, the team responsible for your misery in the last 2 days. And actually, to answer some of the earlier questions, no, there will be no tomato throwing and no stoning, sorry. Okay, let's start with the explanation and details on CTF tasks. For each task, we have actually 90 seconds and up to three slides, and 2 exceptions. There are 2 exceptions, but apart from that, it will be done like a lightning talk on each task, basically. Anyway, so please keep in mind, especially for new CTF players, that for each task there might be a different solution which we didn't think of, or which we thought that it's not really likely that a team would choose and go for. That being said, it's quite probable that some teams solved our tasks in a little different way than we predicted, and the way that is described here. Okay, so Jagger, please take it.
All right, so it's a simple sandboxer. It uses ptrace, obviously, and it spawns additional process in DMP and executes it and sandbox it, right? So first of all, you need to get a remote code execution in your process, and you need to deliver URG signal, right? You can do it by setting so-called urgency flag in the TCP packet. You can do it in your client code like that with MSG OOB. That's a process also inherits a file descriptor, which is open with this flag, so it's not visible on the file system, but you can still write to it. And you can write their ELF binary, which should be 64-bit, and then and write syscall is allowed in the policy. And then you can use a trick with switching your code segment, so you can execute 64-bit syscalls. And then you should use linked, which will make this hidden file appear on the file system. And then you should close this file because you will never execute it because the system will throw xbusy because you cannot execute the files which are open for writing. And then obviously you should use execv 64-bit syscall, which is also allowed in 32-bit policy, right? And the trick is that there is a ptrace call which gets a different size of the register structure. With 32-bit processes, it always returns a structure which is 68 bytes or something like that. With 64-bit processes, it returns something of 200 or something like that. And it overflows a structure inside the sandboxer. And if you set the instruction pointer, initial instruction pointer to certain addresses, then this function pointer will be overwritten, and you can execute your code, right? So in order to set this instruction pointer to the correct address of our gadget, and there was a gadget, execv binsh, you should use these GCC instructions in here, right? You can use different kind of linkers or something like that, but you should set the entry point of your binary to IP address which is execv binsh in your sandboxer. And that's basically it. And I was thinking it's simple, but apparently nobody solved it. But but I know that there's at least one team was very close to that. Right, that's now the second task is basically Stega. I know that you hate Stega, but yeah, I was forced to do that. So basically simple things, right? Up to getting to the binary, which is PPC 64-bit in Little Endian. And then in PPC, you have this idea of branch predictions, right? You can see it in here. So those minus signs mean that the branch will not be taken, probably. It's a hint for CPU for optimizing the pipelines. And plus means that it will be probably taken. So you should look at the code, at the values which are loaded into those registers, like R0, right? And this comparison instruction, and then figure out whether this prediction is correct or not. If it's incorrect, you should add 0 to your bit stream. If it's correct, you should add 1, right? And well, that's it. You will get a base 64 string which you can turn into your flag. All right, I guess that's it.
Okay, Thank you, Robert. So my tasks are the next ones. First one was turbo crack me for 100 points. It was the reverse engineering challenge. It was text mode, VGA, and Turbo Pascal. That's free. So the task was to make our red logo, which was red, to make it green again. And you had to enter a password to make it happen. Now, in VGA mode, actually, to change the color of something, you have to interact with these ports, like 3C8 and 3C9. And if you looked for it in IDA, there actually was only one function interacting with these ports. And it was called in a couple of places, basically in two other functions. And the place you are interested in were the top functions, which one of them set the palette entry, so the logo entry, basically to green, and the other set it to red. Now you had to trace back where what does the jump depend on, and actually you would reach a function which would do a set of simple XORs and XOR checking, which was super easy to reverse and get the flag. And the flag was text mode for the win. The second challenge was core, which was reverse engineering for 300 points. Basically, you got a PHP binary, unstripped with full debugging symbols, and a PHP core. Now, the core was dumped in the moment just before execution of a script, and that meant that you have all the bytecode prepared in the memory. So you had to just open it in GDB and do print, op, array, opcodes, and just go from 0 to whatever, and it would print you the bytecode. Now you needed to reverse engineer this in-memory bytecode of PHP to something more readable, like PHP. And you'd get quite a lot of code, but including something like this. This was basically reading your input, and then doing an MD5 sliding window, reversing in doing a string reverse on the hex digest, and adding it to a final flag. Well, actually final sum, and the final sum was like this thing. So you had to, again, reverse it and then find some MD5 collisions there, which was rather easy because there were at least 2 dictionary words, and you also knew the flag began with dragons and then 2 unknown bytes, but 2 bytes are super easy to brute force. So having just one MD5 sum allowed you to do a brute force 1 byte by byte of the whole flag. And the flag was, I'm pretty sure everyone loves PHP engine internals. Now, this was reverse engineering 500, and I'm really sorry for this task. However, I'm really amazed that somebody solved it. It was a virtual machine written with Turing-complete ROP. So basically, there was a return-oriented programming program which implemented a virtual machine engine, and then that implemented the final crackme. This is a dump of a piece of the return-oriented programming program, which was basically, I think, like 1,000 lines in the end, 1,000 gadgets. But you could reverse engineer it and get the opcodes, and once you had that, you understood how the virtual machine works. You just get to basically solve this virtual machine crackme, which was, I guess, super easy because I didn't want to make it hard at that point. And when you got the flag, it was, what the heck was that? Okay, and now for something easier, which was MISC for 100. You got a zip file, and it was said that the zip file contains a super simple password, but it was encrypted with a super long password. Now, well, you knew that the file length was 11 bytes. You also knew that the beginning and end of the flag was dragons and the curly brackets. So that gives you 7 characters already, and you're only missing 4. Now, the CRC and zip in the header is actually of the crypted data. It's not of the encrypted data, which means that you have the CRC of the real flag. So you just have to brute force the additional 4 bytes, and the flag was dragons zips. Okay, and that's it. VND. Please take over.
So hi, a few words about spoon, knife, and fork. It was a pawning challenge worth 200 points. And as you can see from this code, it's the simple stack buffer overflow code. with the exception that it worked on a machine with NX bytes, ASLR, and a stack protector. So it was a little bit harder. Okay, and as you can see, it worked like an echo server, with the exception that it behaves like the PHP function HTML special cars. So it encodes the quote and the ampersand symbol and two more. So the buffer is 1,000 bytes long, so we can easily overflow it. And here you can sample in and sample out. And the solution to this one was to brute force the stack cookie byte by byte, just by connecting over and over again, because this server forked, and each child of the parent process has the same layout of the memory. So you can, so the cookie was always the same, and this way you can brute force the cookie, then brute force the return address, find the libc address, and use return to libc technique to just cut the flag that was on the same directory as the executable was running. So you can also use the return-oriented programming here. Boost was really useful in this case. It wasn't so useful in case of reverse engineering, but yeah, and that's it. And you can see the flag ball. So thanks. Karim, your turn.
That was hello. That was my first Pwn task. The task was named So Serious Crypto, and was implementing super serious crypto machine. It was there was a ASA inside, and you were able to encrypt some static string or decrypt a string that you provide. The core of the task was AES padding. So AES padding is used to pad the blocks of input data to 16 bytes. So if you have some data, this how it looks inside the memory. And after that, there was a function that stored is password bad set to 1. And user input, and you were able to override the variable on the stack just by brute forcing the padding of the plain text. So this is the flag. Another task pollution. It was forensic 200. You get the pickup file on the beginning, and there was a SMTP inside. So if the task description said that some keys were locked. So if you just Google for or use a DuckDuckGo or any other search engine for keylogger that supports SMTP, you get the proper software. So Ardamax was the proper software. So this is the awesome software, that awesome keylogger that allows you to send data over the SMTP. So the workflow was very simple. You just extract the mails, SMTP sessions from pickup. You extract the files from the emails that was sent, and also just to open those files, you need the password. The password was the same as SMTP out. So you put it all together, and you got all the data that was logged from the keyboard. And one more thing you need to do, the keystrokes were logged among the, I don't know, 5 or 6 notepads open. So you need to just trace the correct notepad instance to get the flag. So it was the flag. Show me your logs now. Okay, Ghost challenge, because Mavak is not here. So we, when he's giving us the task to the test, we are asking him, okay, Malek, is it another 0-day PHP 0-day? No, of course not. We know it. I know it for over a week. So it was not a 0-day this time, luckily. So this is the task description, and you land on the website with index.php. So you need to focus about this hint, and you can find the index.php source code. What was the special in this source code? So first of all, you can inject the data, do a SQL injection from by using a cookie parameter. Second of all, whatever you do in the SQL query gets unserialized. So this is pretty much. You got a call of some method of your unserialized object, and there's also an admin panel that is only accessible from localhost. Inside the panel, you can also leak the source code of the panel by using the same method. So the Vim hint was very useful. You see that the flag is generated using SQL query and printed to the output of PHP. But yeah, the first thing you could convert your SQL injection into a serialized object to get output. Second, you can make a SOAP client object, and yeah, if you call the undefined function of this unserialized object, this object is performing a HTTP request. So this way you can request the admin panel from localhost, but you will not get output of that. Yeah, so luckily you can try to find what kind of SQL query is running inside SQL by doing SQL injection in the same time and getting the list of running tasks inside SQL database. And it was the flag. At fear not, it was the SQL query that was running. Euro?
Okay, so I had a Pwn 500 task called Night Sky, and if you do some initial recon, you can see that the binary has all of the protections enabled. So it has full real row and all the other stuff. Also, it is a 64-bit binary dynamically linked, so probably not too big. And so yeah, what the binary does is that it makes it possible for you to manage the sky in terms of creating and editing and removing stars, which are some objects in memory, and also managing constellations, which are sets of stars that you created. So you can manage that, and the two additional options that you could possibly use was to register the program and to use the save to file option to save the current state of the sky to a file. But you could only invoke the save to file option if you registered the program with a key, and the key was not known. It was loaded from a file from the server, so it was a secret key. Okay, so there are a few bugs in some of those available operations that you had to chain in order to get the task done. So the first bug was in the edit star command. You had to take advantage of the fact that the structure describing a star had a static buffer called name, and even though most of the operations that operated on the name of the star did null termination of the name, this one function didn't. So you could have a non-null terminated name, and directly after the name was a pointer to a constellation assigned to the star. And as it turns out, the constellations were placed in static memory. So by using this bug, you could get the pointer to static memory. And interestingly, you could also specify a name of the constellation, and it also resides in a static buffer. So you would automatically get an information leak of a pointer to static memory with control data. And this is an example of what it looks like after you do this and then issue the list stars command, which shows you the leaked bytes in the output. Once you had this, you had to use a second bug, which was a stack-based buffer overflow, but it was pretty specific. You couldn't really control the size by which you overflow the buffer, because it's a corner case where you specific n equals 0, and then you really read n minus 1 bytes, which in terms of having a 16-bit variable means 64K. So you could trash the stack by a lot of data, but you really couldn't control by how much. And since the stack protector was enabled, you couldn't overwrite anything meaningful, really. You couldn't get code execution because the stack protector would trigger before the return address. And also, the special environment variable called libc fatal std was not used in this task in our environment. So you wouldn't get the message with the stack protector failure back to you in the default configuration. But as it turns out, since you control all of the stack and you read so much data into it, there's nothing to stop you from really setting the environment variable by yourself. So you could just set the NVP pointers to the libc fatal std string, which you could have placed in static memory, which you know. And then you could set the argv0 pointer to the address of the secret in static memory, which was needed to register the program. So you could trigger this memory disclosure this way, and then you could leak the real program serial that you could use to register it. And the third bug, once you had this, you could trigger the save to file option. And this was another stack-based buffer overflow, but it was easier to use because you really control the size of the buffer that you read into the stack-based buffer. And I placed some function pointers on the stack before the stack protector, so you could overwrite them easily. There were 4 functions that were operating on the file that you could specify. And so this means that you had control the IP via one of the overwritten function pointers. And since you already knew the base address of the challenge, because you had it from the previous information leak, you could just probably create a ROP chain or something and solve it this way. Although I'm not sure how many ROP gadgets there were in the binary because it was pretty small, because it was dynamically linked. But there was also an easier solution. So if you look into the provided libc, because we gave it to you, you could see that the canonicalized filename function is in fact in the very same memory page that the system function. So these 2 functions are really very close to each other in the libc. So what you could do is, instead of overwriting the whole function pointer, you could just do a 2-byte partial overwrite, and you could set the 12 bits that are constant to the correct value, and then you should have only brute force the 4 remaining bits, which is 16 combinations. So that is definitely doable over the network. And so yeah, this is how it looked like, and the flag was SSP memory disclosure and partial overwrites for the win. And that's it. So now to Mac.
So SCIS was a simple task for reverse 200, I think. It was handwritten ELF. The biggest problem of ELF is it's kind of dual, because you have both page header. You have headers for sections and for pages, and most of the tools are using the second one for the sections, and they are not actually what's executed. So if you shifted them a little bit, you have something very strange. So the basic was that you have what you saw. You're executing some ptrace anti-debug, and there was a RC4 for brute force, like 4 bytes of key, so you can just brute force it. But behind of this, there was something else that was happening after, and was trying to get information from command line and store it with some static data to check it if it's correct flag. So if you provide it, you have to both brute force the RC4 and get the simple key that was, I don't remember right now. You have to provide it from command line, and that's all. So yeah, just this. Redford?
And going back to that Mac challenge, there was a funny thing because it exploited one bug in IDA accidentally, because it was the IDA, even if you selected load from PHD instead of SHD, that's second header, it still loaded the wrong code. So you couldn't see the correct code under IDA. Okay, so now main task. The task was, the main code was simple. It just checked the flag. But that function was pretty complicated. If you dump the code under, for example, debugger, you can see a lot of junk. It starts with a jump and the whole code is shattered. So you could just read that. It's 30,000 of lines of assembly. And the original instructions were morphed, and there was really a lot of junk code. So you could record execution trace and then implement some optimization like register tracking and removing junk code. Then unmorph the code because the morphing was really simple, and just read the checks. But that's a time-consuming solution. So, but there was more tricky solution. You could record 2 executions of the traces with different passwords, different flags. For example, you enter some text, change one bit for example, in first byte, and compare the traces. And the execution path was always constant, but if you log the register values and see the differences, you could easily spot the algorithm, and just you could easily see what's happening. So that was really easy to do, but a bit tricky. Okay, the second task, encrypted PNG. So you got the file encrypton in Python, which splits the input file into chunks with unknown size, and they get encrypted. So the algorithm was multiplying with k, XORing, and then reversing that multiplication. And every block, the key was taken to the next power. Okay, that was the algorithm, and how to solve that. And you got you saw the algorithm and the encrypted file. So first step was to find block size. That was easy because if you see the encrypted file, there were really a lot of repeating patterns, like that byte which repeated every 7 bytes, because that was the encryption was poor, so especially in lower bytes. Okay, next step was because we know that the PNG file from the extension, we could guess the first 2 or 3 blocks because that was a constant PNG header. And then we got some equations, and next we could just solve that starting from the starting from the lower bits, because the equation was the modulo was in power of 2, so you can start with lower bits and then extend the result, then check key base and just recover the image. So that's all.
I think it was a pleasure challenge because it was something like a crypto for 100 points. And if you exactly look at the challenge, there was very a lot of repeats in the columns. So the main thing of the challenge was to just convert it from all hexes values to the binary. And I don't know how it looks like now, but when we just delete all the zeros, there was a flag in plain text in just visual crypto.
We had two RSA challenges with very similar source code, but totally different solution. And the problem with simplest one was a small public exponent and repeated messages with really small difference. And these conditions are enough to run coppersmith shortpad attack. So just implement solution from paper and get the flag. The harder RSA challenge had something like two parts. In the first part, we should recover a Python internal random state, and we are able to do that by decoding all encrypted random numbers. And since they were very small and public exponents were also small, to decode them, we need just to compute third integer root. There's also not the crypto problem, but some implementation bug in a function which generates random numbers, and this function always return last 320 less significant bits with zeros, and so this amount of bits of first prime number only depends on Python random generator, and since we had its internal state, we are able to find some possibilities of these bits, and having that, we are able to run another coppersmith attack from the paper and get the flag. Kuczyk?
You know this is not how you pronounce it, but I'll let it slide. This task was a hardware task. You might have noticed it on our organizers table. Long story short, accepted a 50 zloty banknote, and it would spit out vodka for you. But that's the lame part. The more interesting part is that if you looked at the photos, you could deduce an architecture. And while a sucker would just pay for the vodka, a hacker can get it for free by possibly interfacing with whatever the SMS functionality in the hardware was. The task was split into two parts. The first one was just for people to understand how the comms worked. So you were supposed to send a command and you would get the flag back via SMS. The second one was you were supposed to pwn the task via buffer overflow via SMS. The same function was responsible to get both flags. When a SMS was parsed for commands, first of all, you could easily deduce the so-called encryption used to decode the buffers. And if you were to write an SMS code that would pass these checks, you would just get the flag back. The same function had a bug where there was a just simple buffer overflow. The decoded array you can see there was 16 bytes long, and it would just get smashed with anything you sent to it but decrypted. So you were able to overflow it with the return address of a function that would just spit out the vodka. As you can see on the right-hand bottom side, corner, my exploit was very simple. I saw people trying to solve it in a more difficult aspect, but if you were just to take the the return address of the vodka function, repeat it as many times as you can, send that. That would trigger the pour. Of course, another thing is that people didn't notice that these were in thumb mode instructions. So you had to increase the address by 1, which was not obvious to people who exploited ARM for the first time. Closing thoughts, right? Oh, of course, here's my plug. You can get the source code and the hardware design of my GitHub if you want to. It's GPL licensed. Hooray. Good? Oh, where's Gun? Oh, good.
Okay, so yes, the authors of the tasks were here, so you could see them, and if you have any more questions, just talk to them. Also, yeah, be sure to come to the awards ceremony, which is going to be in half an hour. And also we have some remaining Programmista magazines laying on our desk. So if you haven't done that yet, be sure to grab a copy. And yeah, thanks for coming.